All right. So that was definitely a thing that happened. So let's carry on with this discussion of set theory. So, um, the next thing that I want to mention is the idea of the empty set. And I know we mentioned this last time. So the empty set is the set containing no elements. And notice that totally describes the set. It's the set that has nothing in it. If there's another set that has nothing in it, well, then those two sets that each have nothing in it, well, they both contain the same non-existent elements. So the empty set really is the empty set. Um, I'll have two notations for it. Sometimes I'll denote it with a zero struck through. Other times I'll use, well, like set builder notation. It's the set with no element, so you don't list anything. Well, if I have two sets, A and B, these two sets are called disjoint, so this is a 2-for-1 definition. I'm defining two things at once. If their intersection is empty. And maybe here's a good example. If A is less than B is less than C is less than D, let's show that AB and CD are disjoint. So let's write down the setup. Start with the assumptions. Assume A is less than B is less than C is less than D. So the assumption of the claim. I need to show that these two things are disjoint. What's it mean to be disjoint? It means their intersection is empty, contains no elements. So let's proceed by contradiction. What does it mean to not contain no elements? Well, that means it contains some elements. And that's the standard way to proceed by contradiction, right? If you want to prove something by contradiction, you assume that the thing you wanted to assume is false, that you wanted to conclude is false. So I want to show this contains no elements. So if I proceed by contradiction, I will assume that AB intersect CD is not empty. It does contain some elements. Well, since it is not empty, there is some X in the intersection. Neato. All right, so let's proceed. I know that there's an X in that intersection. So by the definition of intersection, A is less than or equal to, nope. Definition of intersection. Don't do two steps at once. X is in AB, and X is in CD. Well, by the definition of intervals, that means A is less than or equal to X is less than or equal to B, and C is less than or equal to X is less than or equal to D. And remember, I want to get a contradiction. That's my whole goal. So think about how to get this contradiction. Go and do it. So pause this video for a moment and do that. All right, so either you succeeded or not, both fine. Let's try to come up with that contradiction. So I haven't used this assumption yet. Let's use that assumption. So let's off to the side, do a little bit of scratch walk. So I know A is less than B. Let's give myself some vertical space too. A is less than B is less than C is less than D. I also know A is less than or equal to X is less than or equal to B. And I know C is less than or equal to X is less than or equal to D. Oh, well, that's a problem, right? It looks here like X has to be strictly less than B, and B is strictly less than C, so X has to be less than C, but I know X is bigger than or equal to C. There's a contradiction. And like, that's totally unreadable right now. If you just saw this and someone told you that that was a proof of something, you would say, no, it is not. It is a mess. But we remember the ideas. So let's write them out. So since X is less than or equal to B, and B is less than C, strictly less than C, X has to be strictly less than C. This contradicts that C is less than or equal to X. All right, so we've reached a contradiction. Thus, the assumption that A inter AB. Sorry, I'm doing this slightly after I should really be getting ready to go to bed, as it says 7:45 at the top corner. CD is in fact, this contradicts the assumption that this is not the empty set. Thus, A, B intersect CD is empty. And let's just go ahead and strike that out because I've already reached the whole end of the proof. Groovy. So the last thing that I want to do is some properties of sets. So these will now be just abstract sets that will prove some things about it. There won't be intervals or anything like that. They'll just be sets. And we'll go through some of these proofs. So here's proposition 1.1.10. For any sets A and B, the intersection of A and B is contained in A, which is contained in A union B. And let's prove this. And we have so few assumptions that the proof can't be fancy. Let's start with the intersection is contained in A. So I want to show that A intersect B is contained in A. Well, let's start the way you have to. Let's consider any X in A intersect B. And let's remember the goal. The goal is X is in A. So let's try to get that. So let's start by unraveling this intersection. It's the only thing we can do. By the definition of intersection, X is in A, and X is in B. Oh, wait, but I literally just said the thing that I wanted to prove. So let's just notice that in particular, X is in A. Thus, X is in, thus A intersect B is a subset of A. Next one, A is contained in the union. Well, let's consider any X in A. Let's think about what we need to prove. The goal is X is in A union B. Oh, well, what would that mean? That means we need to show either X is in A or X is in B. But remember the nature of a mathematical OR. A mathematical OR is an inclusive OR. If either of those two things are true, it doesn't matter whether the other one is true. The whole statement is automatically true. So I literally, if I know that X is in A, then I'm done. If I know that X is in B, then I'm done. Oh, wait, but I know X is in A. All right, so since X is in A, in particular then, all right, thus X is in A union B, therefore A is a subset of A union B. And you'll notice that I like paused for a little bit there trying to come up with a different word here. And it's not like a mathematical thing. I just didn't want two sentences in a row to both be thus a thing. Sometimes you just want a synonym for thus so that you don't have too much repetitive language. Oh, nice. So A is contained in B. Since we have A contained in B and A contained in A union B, that's everything we needed to prove. All right. Theorem 1.1.11. These are some more properties of sets. Idempotency. So this is a word that you might remember from linear algebra, maybe not. right? A matrix is called idempotent if A times A is A. Idempotency is generally a property where when you do a thing to itself, you get that same thing back. If a thing has that property, then it's idempotent. So what idempotency means is if you take any set and union it with itself, well, you know what you should get. Should just get A back. If you take any set and intersect it with itself, you'll get A back. Commutativity. Well, you know what that should mean too. What does it mean that addition is commutative? It means you should be able to add in either order and you get the same thing. A union B should be B union A. A intersect B should be B intersect A. Associativity. So you remember the associative law. Multiplication, associativity is moving around the parentheses. A plus B plus C, it doesn't matter where you put the parentheses. You get the same thing either way. A union B union C is the same as A union B union C. A intersect B intersect C is A intersect B intersect C. And if you like, that law associativity is why you can just list a bunch of numbers with plus signs between. It doesn't matter what order you resolve them in. Distributivity. Right, like multiplication distributes over addition. So x times y plus z is x times y plus x times z. Same thing with intersection and union. They both distribute over each other. A intersect B union C is A intersect B union A intersect C. And notice those parentheses do actually matter. A union B intersect C is A union B intersect A union C. So I think I only want to do the distributivity laws. So it's that A, B, and C be sets. We need to show that A intersect B union C is A intersect B union A intersect C. And I might only do one of them just for the sake of leaving something for you to do. And because I've really lost track of time. I'm not sure how much time I've taken up. I guess I'll find out soon. So how do you prove set equality? Well, you need to prove two set containments. So let's prove the reverse one first, because that seems to be like that. That's what the organization is pushing for. It doesn't matter what order you do these two steps. Let's prove A intersect B union A intersect C is contained in there. So I know what my starting point has to be. I need to start by considering any x in the allegedly small R set. And right, there's lots of symbols here. Let's deal with the symbols in the order there. So there's the last thing that gets resolved. So let's deal with that. So x is in the union of those two things. So x is in A intersect B. Or x is in A intersect C. So I think a case-wise analysis is in order. We will walk in cases. And whenever you get to the state where you know that this or that is true, well, you know one or the other is true. Let's assume that one of them is true. Deal with the proof. Assume that the other one is true. Deal with the proof. You know that at least one of them was true, so one of those two cases applies. So let's suppose x is in A intersect B. And let's keep a hold of the goal. The goal right now is x is in A intersect B union C. So what do I need to accomplish that? I need x to be in A. And I need x to be in B union C. Oh, well, neat. I know X is in A, so let's write that down. As X is in A intersect B, X is in A, and maybe I'll even decorate. No, yeah, let's do that. Sometimes it's nice to decorate a statement with some symbol so that you can reference it later. X is in A, I'll label that with a star for later. And X is in B. So let's just flag that here in the scratch walk. This stuff off to the side is not part of the proof. I don't want to see that when you're throwing something in. But it's useful to organize your thoughts. So I need X to be in B union C. Let's think about what would give me that. Oh, neat. I need X to be in B or X to be in C. I know that X is in B. Cool. As X is in B, and maybe I'll even use this instead. And B is a subset of B union C by this proposition, proposition 1.1.10. And that was very quick. Let's make sure I'm using that to say something that it actually says. 1.1.10 says any set is contained in the union of that set with something else. So as X is in B and X is in, and B is a subset of B union C, X is in B union C. And I think I'm not actually going to refer to this star later, so I'm going to erase it. As X is in A and X is in B union C, X is in A intersect B union C. And I find myself running low on space, so I'll close with a sentence that will happen an awful lot in these case-wise proofs. In the case X is in A intersect C, the proof is identical. And I'm writing that, but let's convince ourselves that that's actually true. I'll switch over here to highlighter, and we'll decide how things would have to change. So let's suppose X were in A intersects C instead. Well, then X would be in A intersects C, so X is in A and X is in C. Well, since X is in C and C is a subset of B union C, any set is in the union of that set with itself, with another set. X is in B union C. Well, I know X is in A, X is in B union C. Yeah, the proof is actually identical. So that maybe I'll add this little interjection. In either case, X is in A intersect B union C. We conclude that A intersect B union A intersect C is contained in A intersect B union C. And maybe I'll pause here and I'll say, nice. And you know what? I'm noticing we've already talked about set difference, but let's write down that definition again. In set builder notation, A set minus B is the set of all x's such that x is in A and x is not in B. So it's everything that's in the first set, not in the second. Sometimes you'll also see the notation A minus B being used. I'll try to avoid that notation. I'll try to. I might accidentally slip up. But you'll see that in the wild occasionally. So the last property I want to prove for sets is De Morgan's law. If you have sets A, B, and C, A set minus B intersect B union C is A minus B union A minus C. And there's not like, I haven't specified certainly an order of operations for these set operations of intersect union and set difference. So I'll try to be very careful with my parentheses. And A, that's not what I want to avoid. A minus B intersect C is A minus B union A minus C. And you know what? I know that there's this instruction on a previous thing to like draw a Venn diagram and convince yourself of something. I'll do that for this one. So let's suppose you have these three sets. Top one's A, left one's B, rightmost is C. Let's do this by even just shading in what these sets are. A minus B union C. So let's start with, well, there's A. Here's B union C. I want everything that's in A, so in the pink set, that's not in the blue set. Oh, that looks like it's this. A minus B union C. So what I'm about to do isn't a proof, but it's a good way to convince yourself in advance that something should be true. Let's play that same game again. Top set is A, this set's B, that set's C. Let's walk out this side. This time I want A minus B. That was an error. Intersect A minus C. And let's see if that's the correct thing to have done. Start with A minus B. Here's A minus B. A minus C. Here is A minus C. I would like the union of them. Union means I get everything that's in even just one of them. Yeah, those two. Chris, right, I am getting tired at this point. I want the intersection between them. That means I want everything that's in both simultaneously. Now there's the intersection. Yeah, those two look like they're the same. So that's not a proof. That's a picture that's convincing, but it's not a proof. Let's prove one of them. Let's prove that A set minus B union C is equal to A set minus B intersect A set minus C. And notice here it says that like I'm not going to do the proof, but you know what? As long as I'm here talking, I'll do the proof. If you want to walk away at this point and just do it on your own, then come ask me about it at the start of class tomorrow. Well, Monday, I guess, whatever day I'll be back. You can do that. So let's make a start at it anyway. Let's show that A minus the union is contained in A minus B intersect A minus C. All right, so let's start with this. I know that X is in A, but is not in B minus C. Let's write that down. So X is in A, and X is not in B union C. And let's go up here and think about what it is that we need to show. So our goal is X is in A minus B intersect A minus C. I'll put the parentheses in there. Well, let's think about what that would mean. For that to happen, I need X to be in A minus B, and I need X to be in A minus C, independently. What do I need to get that? I need X to be in A, and I need X to not be in B. And I need X to be in A, and I need X to not be in C. So let's look at what we have and what we need. I already have x's in A. Cool. In the first case, I need x to not be in B. So let's try to show that that's true. So let's suppose, for contradiction, that x is not in B. Nope, that's what I want to be true, that x is in B. Oh, wait. But that would mean that as B is a subset of B union C, then x is in B union C, contradicting that x is not in B union C. Thus, x is not in B. Sorry, we assumed for contradiction that x was in B. We got a contradiction, so we conclude x is not in B. The thing that we assume for the sake of contradiction must be false. A similar argument. Actually, you know what? Back up a little bit. Thus, x is in A minus B. A similar argument reveals that x is in A minus C. So x is in A minus B, and x is in A minus C. All right, so that means we started with a thing in A minus B union C. We got it to be in the intersection of A minus B with A minus C. Thus, A minus B union C is contained in A minus B intersect A minus C. And I don't want to put like the little Halmos box. Right, so the symbol you see sometimes at the end of proofs. I think that this is just because a mathematician named Halmos popularized the use of that to indicate the end of a proof. It's called a Halmos box, sometimes called a tombstone at the end of the proof. I'm not really done with the proof yet, so I can't put it there. Nice, but I am done with half of the proof of this proposition, so a quarter of the proof done. If I want to continue showing this set equality, well, you need the opposite set containment. So I'm not actually going to do it, but I need to show that A minus B intersect A minus C is contained in A minus B union C. Yeah. And so the logic will be the same. Well, it'll be similar logic. Unravel the definitions, figure out what you want to prove. If you want to prove not something is true, maybe proceed by contradiction. Cool. And with that, I will conclude the go through of the first section of these notes. Maybe I'll discuss the homework. So the homework consists first of nothing fancy, just write out what these sets are. I'm not asking you to prove your answers, but they better be right. So you should be confident. Prove one of these De Morgan's laws. A minus the intersection of B union C is the union of those two differences. And I think your proof may well feel a lot like this. In a different order, but it'll feel a lot like that. Finally, prove this. For any sets A and B, A union B is equal to A if and only if B is a subset of A. This might be the first if and only if proof we've seen. You've seen some in the past. You need to prove two subclaims. You need to prove if this is true, then that is true. If that is true, then this is true. And since this is maybe one of the first if and only if proofs, at least in this class, many of you have seen them already in the past. On the next page is the proof of a very similar looking claim. Maybe look at this and get a model for how a proof might look. All right, and we will start here on Monday. All right, thanks so much for your patience in all of this. I'll look forward to seeing you soon. Ask me questions whenever it is that you want to. Thanks for your time.